Hello, I'm Shiraki. I will talk about extending the stepwise levitation height range of a non-contact stage with suction hold. I will start with the introduction. Incompressible floors, a low rate number are common in our surroundings. Analytical solutions have often been obtained for such low rate number floors. Similar conditions arise widely around everyday environments and transport vehicles and inside fluid machinery. So characterizing such flow by numerical simulation is meaningful. As an engineering application of low-range number flow, non-contact air stage equipped with suction hoods have recently attracted attention. These devices use airflow to regulate inferior materials for contactless gripping and conveyance, and the retention hard response is inherently unstable. The uncloseness of levitation height, especially specifically the transient response and its characteristic time scale during conveyance after a step change, remains to be clarified. If the time history of kinetic energy can be approximated using evolution equation, yielding a positive time scale for convergence after a step change, that would be highly useful. Simulations also allow us to explore levitation height conditions that are difficult to realize experimentally, enabling larger step changes and the possibility of new insights. This study aims to extend prior work on the step change problem for the levitation height in the non-contact air stage with suction holes. We enlarge the range of step magnitude and uh, systematically examine the trend in the spontaneous response of the internal flow field. As shown schematically in figures of previous work, supply holes and suction holes are arranged alternately and uniformly, yielding an expected flow symmetry. We therefore analyze the smallest repeating unit, one supply hole at the center, with the four suction holes at the corners, using a periodic boundary condition. With the nominal repetition height of 50 micrometers for the real device. The bulk Reynolds number is 200 with kinematic viscosity. Because the bulk Reynolds number is well below 1000, the nonlinear convective term can be neglected from the viewpoint of both of the flow field and the lubrication type approximation. Accordingly, we solve the incompressible continuity equation coupled with the Navier-Stokes equation with the convective term dropped. The solver is based on a high accuracy scheme with a track record in direct numerical simulation of incompressible turbulent flows. We set the step change range for the uh, relative to the post-step reference height. The first step lower bound reaches minus 70%, as shown in this figure. To realize the step change, we first compute the steady flow at the first step height. The solution field is then used as initial condition at the post-step height. Even at the lower bound height, the gap remains much larger than the mean free path of air, so the continuum hypothesis is valid. The convergence of kinetic energy is shown in the figure A, and the convergence of the spatial RMS of the static pressure change is shown in the figure B. In both plots, The vertical axis is shifted so that the converged value is zero. Both magnitudes are examined with respect to reference height. Uh, the abscissa is non-dimensional time on a logarithmic scale. For both quantities, smaller step magnitude yields smaller initial value. Moreover, kinetic energy takes longer to converge the spatial limits of the pressure change. Following our prior study of a numerical-based theoretical analysis, we represent the time variation of kinetic energy via evaluation equation. Here, if the coefficient Ft in that equation is constant, the genuine convergence is exponential. However, the present results indicate that the observed convergence cannot be captured by a single exponential. Using a power law form for Ft provides an accurate approximation instead. In the present study, we test the power law analogy for Ft with the exponent m treated as a constant as follows. We approximate Ft by fitting it to the numerical result. Figure A and B correspond to cases where the first step height is 50% and 50% of the total step height respectively. The black solid line uh, denotes the numerical solution, and the blue dashed line the fitted function Ft. The power law form reproduces the numerical data well across the extended conditions. Using this if Ft, we derive an approximate solution for the normalized kinetic energy, normalized by its initial value at the onset of the step response, and obtain the associated time constant Ft when matching the approximation to the simulation data. We next test whether the normalized energy function derived from the power law Ft remains valid for larger step magnitude. Plotting the normalized kinetic energy shows that the derived function agree well with the simulation. The time constant obtained by fitting is non-dimensionalized using the viscosity function time vista. Although the non-dimensional how over distal varies with the step magnitude, it remains essentially the same across various number settings, implying that the fourth step transient of kinetic energy is governed by viscosity definition. Thus, the fundamental nature of the phenomenon is preserved as the step magnitude grows, and insights obtained under small step changes are likely to remain valid at larger steps as well. The objective of this work is to investigate the dynamics of the flow inside a non-contact air stage with traction holds under step change in levitation height, extending prior studies to larger step magnitude. The numerical method was a problem approach used in direct numerical simulation of four-bounded turbulence. As a result, the approximate expression for the normalized kinetic energy response agree well with the simulation, and the fit time constants show the same trend as in real work. That's all for my presentation. Thank you for listening.